Hello everyone. In this video, that is the first video that I will be speaking in English. So sorry for all my subscribers that usually watch my content in Spanish, but the idea right here is to reach as much people as possible. You can activate the subtitles options and translate them. So basically, today we're going to show how to connect, how to link Matlab and Aspen Plus. I will be showing it for Aspen Plus version 10, but I will also show you how to do this procedure for a higher or lower version of Aspen. So basically, the first part is show what we need. So first of all, we need a converge simulation in Aspen Plus that has already, you know, converged with results available. In this case, we have a simulation for a case of urea production, and we need an Matlab script that is done in the editor. So basically what we're going to do right now is to place the Aspen Plus backup file of that simulation in the same file as the one with the Matlab script. So in this file that is called OPT, we have the OPT backup file of the Aspen Plus simulation. Can see right here that that is the name of the simulation, and also the script one, which is called final. After that, what I will be showing you is the lines of code that you need. So the first thing is that here in Matlab, everything that's with this percentage symbol and is in green is a comment, so it is not affecting the code. So the first thing is to open Aspen to create a server. So in the case of version 10, we have to place a 36.0 right here, but if you have version 11, you can use 37.0 or 35.0 if you have version 9, and so on. The next thing is that we're going to take all the attributes of a file, and then you have to place the simulation name that you have. In this case, it is OPT, but in your case, you will have to modify this code and also modify this part if you have not version 10. After that, we're going to invoke Aspen, which basically is going to open that BKP file. And right now, we're going to make Aspen to be not visible. This means that if you have Aspen closed, it can retrieve the information from Aspen without opening, and without opening in the front end Aspen, so without showing you that Aspen is open. This is going to be very important for things like speed of your simulation and speed of the to reduce the running time of your code. But we are going to also turn Aspen visible, so make this equal to 1 to show that it is actually placing the variables in Aspen. So the idea of doing a link between Matlab and Aspen is that you can tell Matlab which the variables are that you want to change in your Aspen Plus simulation, and then run Aspen Plus, and after this simulation has converged, you can retrieve all the results, or well, the results that you want from Aspen, and send them back to Matlab. So after that, line 12 is something that suppress Windows dialogues, so that you don't have all that garbage in your computer. So basically everything right here is commented. The only line active here is line 25 that asks Aspen to assign to variable f3 something. So we're going to be showing what is doing right here. So for instance, if you want to know what the mass flow of stream 3 is after the simulation converged, you can go to stream 3, see that stream 3 has a mass flow of 4.2 times 10 to the 6th kilograms per hour as a mass flow. So if you want to take that value out of the simulation, it is an output value because it is a value that the simulation is calculating. It's not something that you gave as input. So you're going to go to customize, and then you're going to open the variable explorer, which is going to open this thing right here. So you're going to open root, then data, and after that you're going to go to streams because it is a stream variable. If it's something like a variable from a distillation column, just as the reflux ratio, or it is a variable of a reactor like the conversion, or an absorption tower like the number of stages, you're going to open the block file right here. But now we're going to open the stream ones. We're going to look for number 3, which is the one that we're interested in, and right here we're going to go for the output one because it is something that the simulation is calculating. Right here we're going to look with a lot of patience what the mass flow, where the mass flow is. I already know that is this one called mass flow mixed right here. So you have to open this and then go to mixed. So the only way to know if it is actually the variable that you're looking for is looking for what the value is. So this is going to tell you 2 things. One, you're going to confirm if that is the variable of interest. And secondly, you're going to know if it has the decimal place, the units, that what the unit of this measure is. Because you cannot change it. You cannot tell Aspen, please, I want this variable in, tons per hour. It is already going to give you some fixed units. So in this case, we have, again, this would be 4.2 times 10 to the 6th power. So this is basically the same flow as the one that we have right here. So the units are kilograms per hour. So what you're going to do right now is that in the variable explorer, you're going to copy this one that says call. So you're going to copy that. You're going to go to your code and you're going to paste that. So basically what we need is to add here the Aspen dot application dot tree dot find node, and then you're going to copy all of this right here and you're going to paste it right here. I already have done that. Then you're going to place a dot in the and write something like body. So if we were to run this line of code right here, it should retrieve the value of the mass flow of stream 3 in kilograms per hour. So this is going to take some time. Matlab is already busy. This should be not that long. But for instance, if you needed this value not in kilograms per hour, we already have it right here. So if I do F3, you're going to have that we have 4.2 times 10 to the 6th power. And if we didn't want it in kilograms per hour, just say like something like kilograms per second, you will have to divide this value by 3600. So that is going to convert that variable to what you need. Now that I already show you that, I am going to close. Yes, I should not. No, I should actually leave this right here to show you that that OPT file has also a reactor, which is right here. And this reactor has a reaction conversion of reaction number 2 of 0.326069. And I want to show you how you can change that value from Matlab. So that value right here is 0.326. I'm going to write that. Well, it is already written right here. That value is the one that we have in our simulation right now. So right now I'm going to close this simulation. I'm not going to save changes on this simulation. And I want to show you how I can change that value. So I'm going to comment this line. And now I am going to activate the change that I want to do, which is assign to variable x a value of 0.32996, which is, different from the value that we already had. I am going to make Aspen visible in this case to show you. And I am going also to open this line of code that basically is doing the same as the one for the stream, but you can see here that we're going from data not to strings but to blocks, actually reactor 101. And now we're going to input right there in input for conversion of reaction 2, we're going to assign the value of x, which is 0.32996. So right now I'm going to run this. As you can see, I don't have Aspen open, and it should open that file for me. And well, the way in which I find out how this route was the same, opening the customized variables and going right there. So this should also take a while. It already opened Aspen and it already finished. So if you go to simulation, as you can see here, it already says that the input has changed. You can open the reactor, and right here at the reaction, you can see a conversion of 0.32996, which is of course different of the one that we had right here, and is the one that I already placed in Aspen. Right now, if I open this code that says run to Aspen engine, it is going to run Aspen. So I'm going to do right now, I'm going to close the simulation and I'm going to run this. So it is going to take a while again because it has to open again Aspen and do everything. What else can I show you? So yes, basically when we run this, we would expect different values for our output variables, and as you can see here, it opened the simulation, it changed the output, and right now it is running. I didn't do anything. It already run. We have results available, and as you can see for the reactor, we have a different value for the conversion as we already placed that. Okay, so right now with this, you can think of many things that you can do. So you can do sensitivity analysis or many things like that where you change values of variables and then you run your code. Now I am going to just uncomment everything that I had previously commented. So in order to make this in order, I have to do this like this. And so I'm going to uncomment everything right here. And now I am going to make Aspen not visible for what I already told you before. So what this code right here is doing is just it is assigning some variables x, y, and z some values. Then it is going to Aspen and change those values. Those values are the conversion of the reactor. Here we have a split fraction of a purge that we have, and this is the temperature of our condenser in our distillation column. So after he assigns those values, he runs the simulation, and then it is going to retrieve a lot of variables. All of these variables are mass flows, we have densities, we have duties of heat exchangers, reboilers, condensers, work of our pump, a boil-up ratio of our distillation column, a production flow, some temperatures of streams, some mass fractions, and more other things. With all those values, he is calculating the operating costs of the process, which are basically the operating costs of the heat exchangers, reboilers, condensers, compressors, pumps, and then it is going to calculate the capital costs of this process. So it is going to calculate the reactor cost, the vessel cost, the dryer cost, the heat exchanger costs, the compressor, the pumps, the tower, everything, based on the values of the variables that he already retrieved from that Aspen Plus simulation. And after that, it is going to calculate also the raw material costs, which are the cost of the carbon dioxide and ammonia that we need for our process, to in the end calculate the profit of that process. This part of the code is not interesting for the moment if you're watching this only for the Matlab and Aspen Plus link. So this part is not interesting at all. But if you're waiting for the optimization part, it is indeed very, very, very important. So if we run this right here, it should calculate the profit of the process for the case that we are considering here, in which we have a conversion of 32.9%, a split fraction of 6%, and a temperature at the condenser of 25 degrees Celsius. So in the end, it already run. We have, a profit value, which I call that variable FO as objective function of $443.6 million per year. So right now I'm going to talk about the optimization that you can implement in Matlab and work on your Aspen Plus simulation. So for the ones interested in that part, here it begins. So what I want to show you firstly is how this genetic algorithm works. So, well, you will need some basics on what a genetic algorithm is, but what we have right here is a very, very basic genetic algorithm where we have a number of generations. We have also a population size, and we have also a probability for crossover and a probability for mutation. So you have to enter uh, all of these values to our code. So for instance, we're going to be using right here, something like two generations, five individuals per population, a crossover probability of 0.8 and a mutation probability of 0.2. It is important that the product between the number of individuals in your population and the crossover, which in this case it would be 4, it is important for this number to be even, okay? After that, it is also important to know that the code that we have right here is programmed for 3 optimization variables, and that you have to give to the code the limits of those optimization variables. So you have to give a x inferior, which will restrict the values of x between an inferior and a superior limit. And this also for our variable y and for our variable c. If you want to change this code from 3 optimization variables to 4, 5, 6, or maybe just 2, you will have to dig into the code, but it will be not that difficult once you understand what we are doing right here. So basically, for the case that we are analyzing, it doesn't matter what the units of your variables are, because what I programmed right here is that if, for instance, x, is a temperature that must go from 25 Celsius to 35 Celsius, what it is going to do is that it is going to normalize this variable. So it is going to calculate x as the inferior value, which is 25, plus a normalized variable x, which can only go from 0 to 1, times the difference between the superior and inferior values. So in this sense, you're going to make sure that your variable is between 25 and 35 Celsius, and also that you will have to represent your variable as a number between 0 and 1. That representation of that number between 0 and 1 is going to be done by a column vector that it is going to be, for instance, this one right here, 901. So 901, basically what we are going to do is that we are going to go and multiply 9 by 100, then add 0 by 10, and then add just 1. This is going to give us, 901. And that value you're going to divide it by 1000, which is going to give you 0.9. So basically with this representation, you're making sure that your variable is going to be between 0.000 and 0.999, which is basically between 0 and 1. So that is going to be the representation. Now, how is the crossover going to be done? So this is also valid for variable y and variable c. So in the end, an individual is going to be represented by a 3 by 3 matrix, such as the one that I am going to show you right here. So basically what this thing is saying us is that column 1 is x normalized, column 2 is y normalized, and column 3 is c normalized. So right now we have a value of x normalized of 0.876, 0.543, and 0.210 for x normalized, y normalized, and c normalized, which it is going then to traduce to the actual value of x, y, c with its units so that Aspen can read it. Now, the crossover is done by choosing a column by a random fashion. So if you're going to change the number of variable, you're going to change the range in which that random variable can go. In this case, it can go from 1 to 3, but if you have 4 variables, it will have to go from 1 to 4. So let's assume that it chooses 2 as the variable. So we are going to, it chooses a column 2. And then it will run a random between position 1 and position 2, and basically just say that he chose position 2. It is well, sorry, it goes actually from position 2 to position 3. So just say that it chooses position 2. So it is going to change from position 2 to position 3 to the individual that we are doing the crossover with. And in that sense, it is going to do the crossover. For the mutation, he does exactly the same. He chooses a column by a random fashion, and then it is going to go only to position number 3. And in position number 3, he's going to, well, he already chose a column, so just say that he chose a column 1. So he's going to go for the 6, and he's going to add 1 to that number. If we have 9, we ask the code to not add 1, but to change 9 for a 0. So that is the way in which it is going to do the mutation and crossover operations for code. So right now we can go to our optimization code, which is the one that is right here. And the first thing that we're going to do is change the population size. So we're going to go for a population size of 5. The crossover probability would be of 80% and the mutation one of 20%. The number of generations are already going to be 2. So for the case that I was showing you, X is the conversion of the reactor, Y is a split fraction of the stream, and C is a temperature of a condenser. So here you have the limits of the variables that we have. And after that, he is going to open Aspen Plus in the same way that we already showed. It has Aspen not visible right here. And this is the only time in which this simulation has to do this. After that, we're going to generate a random population of n individuals. For that, we're going to be using a cell, which is basically a matrix of matrices, in this case n matrices, in which each matrix represents an individual that is going to be chosen by a random fashion. So after we have a random initial population, we are going to initiate our genetic algorithm. So this variable d equals 1 is the variable that will be showing us which generation we are. In this case, we are in generation 1. And after that, the first thing that it is going to do is to make the crossover operation. So for that crossover operation, he's choosing two individuals from the initial population by a random fashion. Then it is going to assign some tags to that individuals to then find a column, which is a variable that it is going to do the crossover. Then it is going to find the point in which it is going to do the crossover, which is what I already told you, if it is going to change the last two or just the third term of that matrix. He is going to do that crossover operation, and then he is going to assign those two new individuals to a new population cell, which is called the population cells of the children, which is this cell NH. So it is going to assign that. Once he finished with the crossover operation, he's going to go for the mutation one, in which he's going to again choose an individual at random from the initial population, do what we were saying of adding 1 to the last position or changing a 9 for a 0, and then finishing this children cell with the new population. So right here we have 2 times n individuals for our optimization. After that, we're going to evaluate the fitness of our individuals. So for that, it is going to create a matrix of fitness, and it is going to evaluate the fitness of the of the parents of those children. So it is going to start with the initial population. For that, it is going to find the values of x, y, and z normalized, then introduce them to the actual values of x, y, and z. And once he does that, he's going to assign Aspen the values of x, y, and z, then run Aspen, and after that, he is going to retrieve all the variables that are important to calculate the operating costs. After he calculates the operating costs, he calculates the capital costs, then the raw material cost, and finally the income because of the selling of our product, to finally calculate the profit, which is the same as our objective function for our optimization. Right here, we're going to have our first restriction, which is that we don't want that the mass fraction of water in our product exceeds a limit value of 0.5 weight percentage. So what we do right here is to calculate the restriction and tell the code that the fitness will be equal to the objective function in the case in which the restriction is greater or equal than 0. In the other case, we're going to penalize our fitness of our individual by multiplying by 80% our objective function. After that, it is going to evaluate the fitness of the children in the same way in which it was done for the parents. And after that, he is going to do the selection process. So right now we have a matrix with all the fitness of each of the individuals. So right now we are going to sort this matrix, but we're going to do it also knowing the index of each of the individuals that has each of those fitnesses. Right now we're going to generate a new population of parents. So we create a cell of size n again. And right now we're going to do a selection process, which is done here in an elitist way, which is basically we're going to choose only the n best individuals, the N individuals with the highest aptitude, with the highest fitness. So right now he's going to check this sorted matrix of um, of fitnesses, and he is going to assign those individuals with the best fitness to the new matrix, to the new cell, sorry, which is actually the new population of parents. Once he does that, he is going to store in a matrix what the best value of fitness was, which is actually the best value of our objective function. And it is also going to store what our best individual of that generation was. So that is going to be stored in this best matrix and best int matrix. After that, he is going to rename the variable n as the one of the new individuals and do and increase the number of generation to the next one, and then he's going to repeat everything. In the end, he is going to translate the results of all of those runs to in the end give us a matrix, which is this one right here, that shows us for each generation which was the value of the objective function or the fitness of the best individual, and also what that individual actually was. So right now I'm going to run to clear my command window. I want to clear everything. Right now I want to run this to show you how it is going to show us the results for each thing. So as you can see, it is taking some time, and in the if we change the number of population for a greater one, it will go it will take more time. So here he already show us that he's working on generation 1. The next thing that he should show us is what the fitness of the best individual of this generation was, which is this one right here, for $26 million per year. And he also is going to show us what the best individual of that generation was. So basically this is 0.892 for X, 0.965 for Y, and 0.109 for Z. Then he went for generation 2, the best individual of generation 2, and then the aptitude of that, sorry, the fitness of that individual. And he already finished right here. So if we open the matrix that is called individuals, we can see right here that column 1 is the generation. We already run 2 generations, 1 and 2. Here we have the objective function or the fitness, which is the same in this case, of each of those 2 generations. And we have also the actual value of X, which is a conversion of 32.57%. The actual value of the split fraction would be 14%, and the actual value of the condenser temperature. So well, that was pretty much everything that I wanted to show you. So please don't forget to subscribe to my channel if you like this video, and comment everything that you want. I hope this was helpful. I can also add right here that in the case in which the simulation doesn't run or it has an error, it can make the simulation to fail. The code can fail because of that. So it will be important to think of doing a modification of this code in which he checks that the value that he's retrieving from Aspen is actually a number. Because in the case in which it is not a number, this will not work. So in the case in which it is not a number, ask the code to jump this individual or to assign a random value to this individual so that the code doesn't stop. So that was everything. So thank you everyone.